I'm going to give a demonstration here of a heating curve practice problem. This tends to give students some of the time a problem for solving, so I want to make sure you have all the steps straight in your mind about how to tackle a problem like this. This is a very typical problem. We're being asked how much heat in kilojoules is required to convert 422 grams of liquid water from minus 18 degrees Celsius to all steam at 100 degrees Celsius. It's very useful to have a visualization of this in the form of a heating curve, where we see with the addition of heat over time at different temperatures what phase our material is in. In this case, our material is water. It's common knowledge what the melting point and boiling point of water is. That's 0 degrees centigrade and 100 degrees centigrade respectively. So that's something you would be expected to know. The critical aspect of being successful in solving this equation, one of the critical things is knowing when to use the right equation. We have two equations we're going to put to work. Here we're going to use Q equals ms delta T. Sometimes the S here can also be written as a C. It means the same thing, specific heat. So basically what we're saying here is Q, the energy, equals the mass of our substance times the specific heat of our substance times any delta change in temperature. The other equation that we're going to use is the delta heat of whatever phase change it is we're talking about. In this case, it could be the delta heat of fusion, which is the heat of melting, or it could be the delta heat of vaporization, which is the delta heat of changing liquid water to steam. Notice that we take the delta heat of the phase change and we multiply it times moles of substance. So we have to move out of grams and into moles if we're using this equation. So what we really need to do now is analyze the temperature changes and where we're going to be on the graph for each temperature change. We're also going to need some specific information to solve the problem, so we can look at that as well. But if you look over here on the left, notice that we have an analysis of temperature and phase. So we can literally break this down into chunks and relate it to what's happening on the graph. So let's say in part A, we're going from negative 18 degrees centigrade, at which point we're going to have all ice, to 0 degrees centigrade, at which point the ice is going to start melting. So that would be this part of the graph that I'm outlining right here. And we notice here we definitely have a delta T because in order to get through this part of the graph, we go from negative 18 degrees centigrade and up to 0 degrees centigrade. Now for the next part, B, we actually have a phase change going on, and notice at this point the temperature is not changing. The energy being added is going into breaking bonds, so the temperature does not rise. And at this point, that's when we're going to have to use the delta heat of fusion times moles for our calculation B. Then once everything has become water at 0 degrees centigrade, we're going to analyze another part of the graph. We're going to analyze this part here, where we go all the way up to 100 degrees centigrade. Clearly, we have a delta change in temperature here, and we will use that to do our calculation going back to the equation Q equals ms delta T. Finally, for D here, I seem to have lost some of my writing. I don't know what happened, so we'll put the change back in here. We have a phase change from water to steam, all steam. Notice we don't get to all steam until we're at the end of the flat part of the graph. So we have four calculations to do here. Two of them are going to involve Q equals ms delta T. And the other two, B and D, are going to involve the delta heat of the phase change times the moles of the substance. Now, we should focus our attention once again over here on these numbers. We will use different specific heats depending on whether we're in the solid phase, the ice phase, or the liquid phase. And we will also use different enthalpies depending on whether we're melting, that's going to be the delta heat of fusion, or whether we are vaporizing from water to steam, that's going to be the delta heat of vaporization. Okay, so now we can look at the calculations we would need to set up for each step. So 4 different calculations. A is going to relate to this calculation. B is going to relate to this calculation. You get the idea. This one's going to be C, and this one's going to be D. We are alternating between the Q equals ms delta T and the phase change calculation. So the rule of thumb here is whenever the temperature is rising, you're going to have a delta T, so you put that in. The temperature is not rising if you're just converting the substance from one phase to another. You have no delta T, and you're going to use the molar heat of vaporization that is appropriate to the phase that you're in. In the third calculation, we have 100 degrees centigrade delta T and a specific heat of liquid water, which is higher, you might notice, than the specific heat of ice. And then finally, calculation 4, we're going to go back to the molar heat, this time of vaporization, so we're going to use 40.7 kilojoules per mole. If we do all the work, these are the numbers we get. Now another alert here, public service announcement, is some of these are going to be in joules, given the units that we were given, and some of them are going to be in kilojoules. You do not want to do all this work and then mess up the final step of not converting your units appropriately. Since we're asked for heat in kilojoules, it will be most convenient to convert these two numbers to kilojoules, which I'm not going to show. You should definitely know how to do that by now. Then we're going to add all of these up, because we want the total amount of heat that it takes to raise 422 grams of liquid water from minus 18 degrees centigrade in the ice phase to all steam at 100 degrees centigrade. So this is the answer here. It is 1.29 times 10 to the third kilojoules. There's no substitute for practice. There's examples on my slides. There's examples from your recitation worksheet. So do practice and get thoroughly adept at doing these kinds of calculations, because I think there is a high probability, not sure how I would know that, but I think there's a high probability that one of these problems is going to be on your first exam.